Good day. My group consisting of Ryan Ramchan, Kiran Kangali, Brian Deoraj, and me, Ronaldo Dashat, will be presenting on the potential application of CO2 enhanced oil recovery in Trinidad and Tobago. CO2 emissions and mitigation. Context of CO2 emissions. Global CO2 emissions continue to rise due to heavy dependence on fossil fuels, such as oil, gas, and coal. Major emitting sectors include power generation, transportation, industrial and manufacturing sector all contribute heavily to emissions. CO2 is primarily a greenhouse gas driving climate change and global warming. Increasing atmospheric CO2 concentration contributes to sea levels rising, extreme weather, and environmental stress. Need for mitigation. To meet global climate goals such as the Paris Agreement, large-scale reduction of CO2 emissions is essential. Mitigation strategies include energy efficiency, where using less energy for the same output. Secondly, renewable energy, using methods such as solar energy, wind energy, and hydrodams greatly reduce emissions into the atmosphere. The use of CCUS or carbon capture, utilization, and storage methods, or even switching fuels, such as switching from coal to gas in some cases. Capturing and storing CO2 from industrial sources helps reduce atmospheric release. Mitigation ensures sustainable development, reduces climate risk, and stabilizes long term energy security. Rationale for CO2 EOR enhanced oil recovery. CO2 EOR involves injecting CO2 into mature wells and reservoirs to increase its oil production. The injected CO2 mixes with the oil and reduces its viscosity and improves its flow towards the production well. Benefits. The benefits include increasing oil recovery from depleted oil fields, which extend the life of the field, provides economic incentive to capture CO2, which entails the oil revenue offset capture and transport costs, allows for long-term CO2 storage underground, reducing atmospheric emissions. This creates a bridge between current fossil fuel use and future low carbon systems. This helps industries adopt CCUS technologies by making CO2 management financially viable. Overview of CO2 EOR process. CO2 capture. CO2 is captured from large industrial sources such as power plants, refineries, or natural gas processing facilities. Capture technologies remove CO2 from flue gas or processing streams so it can be stored and reused. This prevents CO2 from being emitted into the atmosphere on a whole. CO2 compression. The captured CO2 is compressed into a supercritical state where there is high pressure and moderate temperature. In this supercritical form, CO2 behaves like a dense fluid making easier and more economically friendly to transport and inject. Compression also increases CO2 density, reducing pipeline volume requirements. CO2 transportation. Compressed CO2 is moved from the captured site to the oil field, mainly through pipelines, most commonly used and most commonly economically friendly. They also use trucks or ships, used for smaller volumes or offshore areas. The transport system must maintain high pressure to keep CO2 in its supercritical phase. CO2 injection. CO2 is injected into depleted oil reservoirs through dedicated injection wells. Inside the reservoir, CO2 mixes with residual oil, reducing its viscosity and swelling, which improves its flow. This pushes the mobilized oil towards production wells to increase recovery. CO2 recycling or reinjection. When oil is produced at surface facilities, some injected CO2 returns with the produced fluids. This CO2 is separated at surface via a separator, compressed again, and re-injected back into the reservoir. The cycle continues, improving efficiency and reducing the need for fresh CO2 supply. Over time, a portion of CO2 remains permanently trapped within the reservoir, contributing to long-term CO2 storage.
Today, I'll be walking you through the main reservoir drive mechanisms that move oil toward a well, the different ways CO2 is stored underground, and finally, two major case studies that demonstrate how these processes work in real industrial settings. Let's begin with the natural and enhanced oil recovery mechanisms. The first mechanism is solution gas drive. Under high pressure, oil in the reservoir contains dissolved gases. When production lowers pressure, gas comes out of a solution and forms bubbles. These expanding bubbles push the oil toward the production well. It's similar to opening a soda bottle. When pressure drops, gas escapes and forces liquid upward. This mechanism is common but not very efficient because the pressure quickly decreases and recovery drops over time. The second mechanism is gas cap drive. Some reservoirs naturally have a pre-gas layer above the oil. This is the gas cap. When reservoir pressure decreases, the gas cap expands, pushing the oil downward and toward the wells. This mechanism is more efficient than solution gas drive because it provides stronger and more sustained pressure support, allowing for a more uniform sweep of oil. Next is water drive. This occurs when an aquifer sits beneath the oil zone. As oil is produced and pressure falls, water moves upward into the reservoir, acting almost like a piston. This water helps maintain a pressure and efficiently displaces oil. Water drive reservoirs often have the highest natural recovery efficiencies, sometimes exceeding 50%, because the water is continuously pushing oil toward the well. Finally, we have gas injection, which is an enhanced oil recovery technique used when natural drive mechanisms are insufficient. Gases such as CO2, nitrogen, or hydrocarbon gases are injected into the reservoir. The gas increases pressure and can mix with or swell the oil, reducing viscosity and making it easier to displace. CO2 is especially valued because it not only improves oil recovery, but also allows for long-term storage of CO2 underground. Gas injection can also be alternated with water, known as WAG, or water alternating gas, to maximize efficiency. Now that we've covered oil recovery, let's move into CO2 storage and the trapping mechanisms that keep CO2 safely underground. These mechanisms are important for carbon capture and storage, especially when combined with CO2 based enhanced oil recovery. The first trapping mechanism is structural trapping. This is the simplest and most immediate form of storage. CO2 is injected deep underground and rises through porous rock because it is lighter than the surrounding fluid. Eventually, it reaches an impermeable rock layer, also known as a cap rock, which stops it from moving upward. This is the same natural trapping mechanism that has held oil and gas underground for millions of years. Structural trapping provides a initial security for CO2 right after injection. Next is residual trapping. As CO2 moves from the tiny pore spaces of the rock, some of, some of it becomes disconnected and stuck as isolated droplets. These droplets can no longer move because capillary forces hold them in place. Even if reservoir pressures changes, the trapped CO2 stay immobilized. This mechanism becomes increasingly effective as CO2 plume spreads and recedes over time. The third mechanism is solubility trapping. Over time, CO2 dissolves into a formation water. Once dissolved, it becomes part of the brine and loses its buoyancy, meaning it no longer tries to rise towards the surface. The reservoir rock can hold significant CO2 depending on how saline the water is and how much contact it has with CO2 plume. This process occurs gradually but improves long-term stabilization. The final and most permanent mechanism is mineral trapping. After CO2 dissolves into the water, it can react with minerals in the rock, such as calcium, magnesium, or iron, to form solid carbonate minerals. This process essentially turns CO2 into rock. Although mineral trapping is slow and can take decades to centuries, it presents the most secure form of geological storage because CO2 becomes part of a solid geological structure. Now, let's take a look at how these concepts apply in real life. The Permian Basin in Texas is one of the world's largest and most successful CO2 enhanced oil recovery regions. The Permian Basin leads global production in CO2 enhanced oil recovery. More than 600,000 barrels per day are produced using injected CO2. This demonstrates the long-term technical and economic feasibility of CO2 enhanced oil recovery. The main CO2 trapping mechanism here is structural trapping, supported by some residual trapping. The CO2 injected for oil recovery becomes partially trapped beneath the cap rocks, and some remains locked in pore spaces as the CO2 plume moves and retracts. While the primary goal is oil recovery, the region also contributes significantly to carbon storage. The second case study is the Weyburn Midale CO2 storage and EOR project in Canada, one of the world's most studied geological storage sites. This project has safely injected more than 30 million tons of CO2 since the year 2000. It is known for its strong monitoring program, including seismic imaging, reservoir modeling, and surface monitoring to ensure long-term containment. Unlike the Permian Basin, Weyburn-Medill features all four major CO2 trapping mechanisms working together. CO2 is initially held by structural trapping, but over time, significant amounts become permanently stored through residual trapping, solubility trapping, and eventually mineral trapping. This makes Weyburn-Medill a global benchmark for safe, multi-mechanism CO2 storage. In summary, reservoir drive mechanisms, whether natural like solution gas drive, gas cap drive, and water drive, or enhanced like gas injection, determine how effectively oil can be produced. CO2 injection not only improves oil recovery, but also enables geological carbon storage through structural, residual, solubility, and mineral trapping. The Permian Basin and the Weyburn-Medill project show how these processes operate in real-world settings, demonstrating both the economic value and environmental benefits of CO2-based enhanced oil recovery.
On this slide, we look at the economic feasibility of CO2 enhanced oil recovery. The first thing to note is that the initial setup costs are high. Building CO2 capture equipment, compressors, injection wells, and pipelines require a lot of upfront capital. However, once the infrastructure is in place, the long-term returns are strong. This is because CO2 enhanced oil recovery can significantly increase oil production from mature fields. Oil that was previously unrecoverable becomes mobile again, which means companies can generate revenue from fields that were declining. Over the life of the project, the additional production helps recover the initial investment. Another major advantage is that companies can benefit from both oil revenue and carbon credits. As more countries focus on climate action, carbon markets reward industries that store CO2 underground instead of releasing it into the atmosphere. These credits can help offset operating costs and improve the project's financial viability. And finally, CO2 enhanced oil recovery creates new job opportunities, especially in engineering, construction, monitoring, and pipeline development. It contributes to economic activity in the energy and infrastructure sectors, which strengthens the overall value of adopting this technology. So, overall, while CO2 enhanced oil recovery starts expensive, the potential for the long-term profitability and job creation makes it economically feasible. Now, let's focus on what this means specifically for Trinidad and Tobago. Trinidad and Tobago has several mature oil fields, both onshore and offshore. These fields are ideal candidates for CO2 enhanced oil recovery because they still contain oil, but natural reservoir pressure is declining. Using CO2 can help push out more of the remaining oil, extending the life of these fields. The country also has reliable sources of industrial CO2, especially in Point Lisa's industrial estate. Industries like ammonia, methanol, and power generation release large quantities of CO2. Instead of venting this emission into the atmosphere, it can be captured and repurposed for enhanced oil recovery. This creates a win-win situation by reducing emissions and increasing oil production. Another key point is that Trinidad has the potential to develop a regional hub for carbon storage and enhanced oil recovery operations. If the necessary infrastructure is developed, such as CO2 pipelines and injection sites, it could serve not only as local industry but potentially neighboring countries as well. This positions Trinidad and Tobago as a leader in climate related energy technology in the Caribbean. So, in summary, Trinidad and Tobago has the right reservoirs, the right industrial sources, and the right strategic potential to benefit from CO2 enhanced oil recovery. Looking closer at actual application, this slide explains how CO2 enhanced oil recovery could be implemented in Trinidad and Tobago. Many of our southern and offshore reservoirs have the geological characteristics needed for effective CO2 injection. These areas already contain declining fields with the appropriate rock properties, making them strong candidates for enhanced recovery. Another important advantage is that Trinidad already has a network of existing pipelines. This reduces the cost of transporting CO2 from industrial facilities to oil fields. Instead of building everything from scratch, we can integrate new CO2 transport lines into the infrastructure that's already there. And finally, this approach aligns with national low carbon development goals. Trinidad and Tobago has committed to reducing industrial emissions. CO2 enhanced oil recovery supports that commitment by capturing CO2 from the power plants and heavy industries and storing it underground. At the same time, it boosts oil recovery, which supports the country's economic stability. So, this slide emphasizes that Trinidad has the right location, the right infrastructure, and the right long term policy direction to make
Regulations and incentives. Before Trinidad and Tobago decides to fully implement CO2 ER, we really need to make sure that the policy framework supports it. This isn't just about injecting CO2 on the ground. It's about regulating how it is transported, injected, monitored, verified, and safely stored for decades. Currently, we have energy regulations under the MEEI and environmental rules under the EME. What we don't have yet are laws specific to carbon management, storage, and carbon utilization in oil recovery. So what we need is an update to our energy regulations that defines our CO2 pipelines, how it should be built and maintained, how injection wells must be designed and tested, what monitoring equipment is required to prove CO2 remains locked underground, and what standards companies must meet before they are allowed to start CO2 projects. To make industry preparations attractive, we need to also set a clear incentives. Other countries use tax credit, low royalties, and carbon credit payments for every ton stored. If Trinidad implements something similar, like a royalty incentive for fields using CO2, EUR, or tax deduction for companies investing in CO2 capture, then it becomes financially worthwhile, not just environmentally beneficial. So regulations provide control and safety, and incentives provide motivation and investment. Both are absolutely necessary if we want CO2 EOR to take off here. Challenges. Of course, as promising as CO2 EOR is, it comes with a few challenges. The biggest one is cost. Capturing CO2 from industrial plants, compressing it into a dense liquid, then transporting it through pipelines is expensive upfront. Even though Trinidad produces a lot of CO2 in Point Lisas, we still need infrastructure to move it to mature oil fields in the south and offshore. Next, infrastructure gaps. We don't yet have a pipeline network designed for CO2. In countries like the US, these were built over decades, so Trinidad and Tobago has to start from scratch to build strategically in phases. We need to ensure our reservoirs are technically suitable. Not every oil field will respond well to CO2 injection. We need core samples, reservoir simulations, and pilot tests. These are also regulatory and public concerns. People may worry about leakage risk, seismic activity, or who is responsible if something goes wrong 20 years from now. If this requires strong, no, this does require strong regulation, public education, and transparency. And finally, profitability. It depends on the oil price trends. If the market price drops too low, companies may be hesitant to invest in new technology, even if they offer long term benefits. So challenges are real, but they're manageable with planning and collaboration. Potential solutions. The good news is that none of these challenges are deal breakers. There are practical solutions that Trinidad and Tobago can implement starting now. A major solution is to begin with a pilot project, not a full scale implementation. A pilot allows engineers to test CO2 gradually, measure results, and collect data. It reduces risk and proves feasibility. We can target mature fields with existing infrastructure, especially in the southern basin. Another solution is to build a shared CO2 hub instead of multiple pipelines. Polynesis industries produce massive amounts of CO2, such as methanol, ammonia, and LNG facilities. So instead of each company building its own pipeline, we could create a centralized CO2 collection and transport network feeding into selected oil fields. These significantly reduce costs. We also need updated legislation that clarifies responsibility and environmental standards. The EMA, MEEI, and even UTT and UE can cooperate to create standards based on what the US and Canada already uses. Education and workforce training are critical. We can build local expertise by adding CO2 capture storage and monitoring training into engineering and petroleum programs. That way, we're not depending entirely on foreign consultants. Finally, carbon markets can make CO2 ER profitable. If Trinidad earns revenue for storing carbon, then even oil price periods remains attractive for companies. So, the main solution revolve around collaboration, shared infrastructure, education, and smart financial frameworks. Environmental benefits. From an environmental perspective, CO2 ER turns a problem into a solution. Instead of releasing CO2 into the atmosphere, we use it to produce oil while permanently storing a large percentage underground. This creates two major benefits: less emissions from heavy industries, cleaner, lower carbon oil production. We also reduce the need for new exploration, seismic surveys, and drilling new wells. This means less land use, less marine disturbance, and less ecological impact overall. On top of that, CO2 ER allows us to repurpose existing infrastructure, such as the pipelines, platforms, and wells, so we're not building more industrial sites. It supports circular economy principles where we extend the use life of what we already have instead of expanding into untouched environments. And the most important one, CO2 EOR helps with Trinidad and Tobago take real action towards climate targets without shutting down our energy industry. It's bridging technology that helps us transition responsibly into more sustainable energy practices. Social and economic impacts. Now, let's talk about people, jobs, communities, and the economy. Economically, CO2 ER increases production from oil fields that would otherwise be declining. That creates new governments renew from the same assets we already own. It also makes Trinidad's oil more competitive internationally, especially as buyers look for lower carbon energy sources. Socially, it creates jobs across multiple sectors, not only in drilling and production, but also in CO2 capture equipment, maintenance, pipeline construction, monitoring technology, and even data analysts. It stimulates growth in both traditional petroleum and new carbon technology fields. This creates new career paths for local students and young professionals. We no longer produce only petroleum engineers, we can produce carbon storage specialists, emissions engineers, and environmental process analysts. Of course, with increased industrial activity, we must engage communities and ensure they understand the benefits and practices. With proper communication and monitoring, CO2 EUR can be a socially accepted and environmentally appreciated tool. Future outlook. Looking ahead, Trinidad and Tobago is in a strong position for CO2 EUR compared to many countries. We already produce concentrated CO2 in Mauritius. We already have mature fields, and we already have oil infrastructure. Very few countries have all three conditions together. As the world transitions to net zero targets, the market will favor oil that is produced with lower carbon intensity. Trinidad could brand its future oil as low carbon petroleum, which gives us a competitive advantage in the global market. In addition, as we gain expertise, Trinidad could export CO2 storage knowledge to the Caribbean region. We wouldn't just export oil, we could export energy knowledge and technical services. CO2 ER doesn't just extend field life, it opens a new pathway for us to modernize and diversify our energy economy. Recommendations: conduct detailed feasibility studies. Before we invest in large scale CO2 ER, we need to understand how Trinidad and Tobago's reservoir respond to CO2 injections. Not all oil fields behave the same, and not all geological formation will store CO2 permanently. So our first recommendation is to run a detailed feasibility study. This would include reservoir simulation, core analysis, pilot injection, and economic modeling. These studies would help us answer a few key questions. How much additional oil can each field produce with CO2? How safely and how much CO2 will remain trapped? Which reservoir are the best candidates, onshore or offshore? What is the cost versus revenue potential for each project? Basically, feasibility studies remove the guesswork and allow governments and operators to decide where and how to start EUR in the most cost effective way. So, moving on to the next one, develop national CO2 infrastructure and incentives. The second major recommendation is to build CO2 infrastructure. Trinidad already produces a lot of CO2 at point source from ammonia, methanol, and energy facilities, right? And most of those CO2 are vented into the atmosphere. If we shared the network of CO2 pipelines and compressors to move that CO2 oil fields in the south and offshore, we could convert our waste emission into a valuable resource. However, no company will build that infrastructure alone. That's why incentives are crucial. Trinidad could produce tax credits for CO2 captures or injection, royalty reductions for oil produced using CO2, carbon credit payments for storage. These incentives make CO2 profitable, not just environmentally friendly. So infrastructure plus financial policy support is equal to the real implementation. Promote education and training in carbon management. Finally, even if we have policies and pipelines, we still need people trained in these systems. Trinidad and Tobago needs a new generation of engineers and technicians who understand CO2 capture carbon technologies, reservoir behavior during CO2 flooding, pipeline and compression systems, long-term CO2 monitoring, and safety systems. This opens up new job opportunities beyond traditional petroleum engineering. We move into a broader energy role. We're not only producing oil, but managing carbon. Universities like UTC and UE can update degree programs, and companies can collaborate on training and internships focused on carbon management. That way, we build local expertise instead of relying solely on foreign consultants. Conclusion: CO2 ER combines emission reductions with oil recovery. In summary, CO2 allows Trinidad and Tobago to reduce industrial emissions while recovering more oil from fields that are already in production. We don't have to choose between climate responsibility and oil revenue. CO2 ER lets us do both at the same time. It turns CO2 from a waste product into a useful tool. Feasibility for Trinidad and Tobago mature fields. We already have the right conditions. Our mature fields in the south and offshore can benefit the most, and our petrochemical industry exactly the type of CO2 stream suitable for injection. So, unlike many countries that must first build capture plants, we already have a head start. Requires collaboration and productive policies. Requires collaboration and supportive policies, but none of this happens automatically. We need collaboration between government regulators, pernicious industries, and oil operators. We also need supportive policies that make CO2 storage safe, profitable, and fully integrated into our national energy plan. If we put right policies, infrastructures, and education systems in place, Trinidad and Tobago can become a leader in low carbon petroleum production, not just in Caribbean but globally. I would like to thank you behalf on our group, and we conclude the session.